Okay, so we're switching our focus from mirrors to lenses now. So you just did a reading on refraction of light, all right? And we want to consider what happens as light passes through something that looks like a typical lens that you may have seen. Now, first of all, some vocabulary. This lens is a convex lens because it's thicker in the middle than it is at the edges. In fact, the edges have gone down to a thickness of 0 for that lens. But down below, this would also be a convex lens. So when you're looking at refraction of light, sometimes you might just be going from air to glass, but with the lens, light will pass from the air through the glass and back to the air again. So this would be a concave lens because it is thinner in the middle than at the edges. And this also is a concave lens. All right, so the last two lenses actually behave similarly. And this last lens looks a little bit more, and the first one as well, looked a little bit more like what you might wear on your face if you need corrective lenses. So there's a very badly drawn eyeball. You wouldn't want to have a lens like the one I have in the top picture in front of your eyeball. It wouldn't be all that helpful for glasses because we need to kind of have the, if I were to put my eye at a point here, we want all of the glass to be about the same distance away from the eyeball. So we want it to curve in a way that would be useful for being able to see. So some of the lenses on the bottom may look more like the lenses of eyeglasses. They all kind of curve away from the eyeball, but you could have a convex lens in front of your eye or a concave lens, depending on what kind of correction you need for your vision, right? But we're going to focus on the convex lens because ultimately we want to understand how a telescope works, and all telescopes have a convex lens as the eyepiece, right? So let's consider a light ray that is coming in to this lens. So let me just put a ray coming in parallel to the optical axis, and it hits the glass right there. All right. Now, some of that light actually does reflect off of the glass. If you look at somebody with glasses, sometimes you catch glints of light bouncing off the surface of their glasses, but we're going to only consider the light that transmits through. So as you learned with refraction, we need to consider what is the normal line to the surface right at the point where the ray hits. Okay, so I sketched in a normal line. All right, now because of the law of refraction, we know that in air, n is approximately 1, okay, which is the same as a vacuum, all right? But when air hits the glass, the index of refraction is greater than 1, probably something like 1.3. And so when the light ray hits it, it literally slows down, and that forces it to bend, all right? It's kind of like if you had a marching band marching, and you could think of actually rows of marching band, that's light actually comes in waves. But if we slow this edge of the marching line, we would see that the marchers start to curve, and that's exactly what happens to the light. So it starts to bend towards the normal because the index of refraction is greater. So the angle of refraction is smaller than the angle of incidence. So that causes the ray to bend down a little bit, all right? So you could see it would be heading towards perhaps a focal point. But then we have an exacerbating effect, an amplifying effect, if you will, on the other side. There's my normal line here. Now, as we go from the glass back to the air again, the index of refraction drops, and so we would expect the angle to go up. So it won't cross straight over, it will cross and bend. So the bending at both surfaces of this convex lens both cause it to bend further towards some point, which if we looked at the symmetry of it all, this would be, should use capital F for the point, the focal point, which is located at some, whoops, let me put my lines here, at the focal length beyond the lens, all right? Now, that focal length can be calculated from complex equations. Well, not so complicated. There's something called the lens maker equation, which is in section 33.4 of your book. So it's not so difficult to derive it, but just in the interest of time, we'll just assume there is a focal length. So based on the curvature of the two surfaces, an optometrist or a lens maker of any kind can determine what the focal length would be. So F, we'll just say for now, depends on, we'll just say R1. We have the front surface has a radius of curvature. It also depends on R2, the curvature of the back surface, and the index of refraction of the glass. Not all glasses have exactly the same index of refraction. So depending on the glass that is chosen, that determines how much bending of the light will happen. So it's simply a function of those things. But we can see in the case of a convex lens that will cause the light to bend towards a focal point. So in general, if I have a lens like this, it's going to cause the light to bend inward, which will help my eye to focus the light on my retina in the back of the eye. We won't have time to discuss the eye much, but your eye itself is a convex lens, which takes the light that's coming in and focuses it all just a couple centimeters away on the back of the eye. So a convex lens would help to focus light. A concave lens, on the other hand, the light that's coming in parallel actually will spread out. And it turns out the focal point when we have a concave lens, which we won't have time to discuss much, is actually on the same side of the lens as the light was coming from. Just for point of clarification, when we start working with the thin lens equation, we expect light to pass through. A lens here, so we expect the light to pass through, so we get a positive focal length when the focal point is on the side where the light has passed. Okay, so for a mirror, we expect the light to reflect. So we said the focal point or the focal length was positive if the focal point was in the side where the light did reflect. Now the focal point is positive when it's on the side opposite of where it came in, because we would expect refracted light to pass through. And if the focal point is on that side, we will say that we have a positive focal length. Okay, so in our next video, we'll start to look at how we form images for convex lenses.